So I'm Andreas Kollegger. I'm actually the current cloud wrangler of Neo4j. This is my good compatriot, Peter Neubauer. Peter?
Yeah, I'm one of the founders of Neo4j. We developed it back in the days in 2001, and now I'm doing mainly like community, engagement and getting people to love Neo4j. And have like a small part of your graph that is like reference data, like all your users, and then you have another part of your graph that is shardable, because these users have data that is just interesting for the user. However, you want to find connected users and their data. So you between like below the users, you actually have like kind of documenty data or subtrees that can have very weak links. They can have links. It's still a graph, but these links don't have to be performant. You can actually cache them over as you need them or whatever. You don't have to have share nothing or so you can apply different techniques on different parts of your data. So much, but we will apply different caching strategies for different parts of your data, which means sometimes there will be a share nothing architecture where you actually go and fetch that thing over there, because it will not be, because that is the master. However, in other regions of your data, you might say this is like a low traffic, low update, good cacheable part of my data that is not that big either. So I want to have it replicated on all shards. The problem is that you have two things to it, or three. You have the graph density, and then you have the access pattern. You might have like a lone node that is like your type node for all the persons, that all the persons are attached to. This looks very, very lonely. Oh, I can shard it. However, every single query goes through that, touches that node. Or you might have things that look like very low access, but they're very highly like contagious when access when it comes to write load and these things. So there's different things. You can't just say that just because this looks like a cluster, it is a cluster.
Right, you have to know what kind of a cluster is that. What is it actually? Again, unless you have some application understanding of like what that signifies, it's hard to draw any conclusions based on it, because you have to, without the access patterns that then do give some hints, some idea about like what probably that thing is. Because within a graph, it's never all the same data. It's some of the data is part of your domain. There might be multiple domains. You might have access control parts of the data, then geographic, and then of course just purely structural parts of the graph that aren't data themselves. It's just a way of actually organizing all the data that's there. And any one of these might end up looking like, oh, that's a very dense node, or that's this region over here seems like it's connected to everything. But you don't know why. The biggest graph in production, isn't it 2 billion nodes in China?
It's actually 10% of Facebook.
I would actually
say that's the biggest one.
That probably has become now the biggest one, right?
Yeah. So there's one customer actually persisting, like whoever comes in there, their Facebook data in Neo4j. That means they have slurped in basically a tenth of Facebook in one single uncharted graph and are doing very fine with it, which is kind of encouraging. Yeah. We haven't tested that at that size, but they are very happy with it. So I would say that's the biggest installation. I don't know exactly the number, but the bigger installations are about a few billion relationships, and then under a billion nodes. Normally, relationships are much more frequent in a graph than the nodes.
The most critical factor definitely ends up being the disk I/O. So because we're fully, we're properly ACID transactions for all of our writes, that means we're, purely bound on disk I/O speed for doing writes. Yeah. And so that's, in a system, far and away the most critical component to have, be the biggest, baddest, fastest disk you can get. And then, as usual, of course, having a lot of RAM around is very nice. That's very helpful because we have great caching schemes for the system.
But I mean, so you're just talking about running on a machine, a compute node that has a bunch of RAM and fast disk access, as opposed to, distribution across many compute nodes to implement, these hundreds of millions of relations databases.
We basically don't need to. These things are running like good, and then we cluster for high availability. So it's basically production stability and read scaling. So Neo4j right now is not write scaling, and that's the major obstacle we want to remove with Neo4j 2.0, which is sharded. So it's not purely for the data size of point of view. It's above all from the write throughput point of view.
The node is what simply we as graph people, of course, that's our data record. Mm-hmm. So that's just as in relational database, you just have a row. We call them nodes, and we have nodes, and then we have relationships. So the classic way to picture this, of course, is circle, line, arrow, circle.
Yeah.
Classic way, right? So, but we're a property graph, which means both the nodes, the data records, and the relationships between the data records can have properties on them, and an arbitrary number of primitive properties. So whether it's strings, integers, things like that, of course, right? And that's it. So with that, that's the basic data model.
Scalar values.
Yeah.
Because if you had any kind of vector values, that would be represented as a set of relationships.
Typically, you end up just splitting that out. You can have arrays of the scalars as well.
And you can of course serialize objects into strings, but that's defying the purpose because you make the data structure again more blob related.
Yeah, you've made it opaque at that point. You can't do queries on it, and so it's a little less useful. We're trying to actually one of the things we're looking at right now is while we do have for the property values that they are just scalar and then possibly arrays of scalar, we're considering approaches for taking if you had a JSON document, for instance, and how we should represent that within a graph. We could automatically just break that onto a couple different nodes and then let you retrieve them as one unit or not. Or we could say that for a property value, that is a nested object that you can still do meaningful queries on when you're doing a graph traversal. There's a bit of debate happening internally now about the benefits of either approach and really what the best thing is for users. Mm-hmm. It's about dealing with the graph as your sort of fundamental unit of representing data. All the stuff that we learned back in CS 101 for data structures all come, rushing back into your head. You're like, oh, wait a second, I've done this stuff before. I remember what a linked list is. This is, okay, we just go ahead and there we go. We've got a list. And of course, all the tree structures and all of that is used pervasively in all data modeling within a graph. So because, of course, within a graph, rather than thinking about schema, you're always thinking in terms of, well, what's the structure of my data? How does this actually look? And we have a query language called Cypher that lets you express that in very nice ways. But what I've just kind of glossed over there, of course, is the node to start with. How do you find that very first node? That's the role that indexes play within a graph, is that when you just want to do a quick lookup, essentially, for the node whose name is Andreas. You go to the person index and you say, okay, give me the person whose name is Andreas. And then there you go, you've got your starting point, and then you do a graph operation from that point. So it's a little bit different than the way indexes are thought about within relational, where it's an optimization for speeding up queries. You don't directly work with indexes. At the moment within our data model, you actually just use an index directly to do a lookup.
Links or relationships between nodes are traversable in both directions because they're actually pointing in both directions.
Yeah.
So there's no speed penalty on traversing in a relationship from both ends. And that means out of if you build up an R tree or whatever, you can actually go in that index structure from downwards up or from onwards down. And while you're doing this, going back into your domain model, check things, and then continue traversal in that index structure. So basically the whole graph is just a big multi-dimensional index in that respect, because everything you do is basically shortening traversals between things as you insert more links. Or that could be actually what we call an in-graph index. You know where to start, or you find oh, this is my index that has its starting point, and it will give you a targeted traversal result in the graph. So yes, that is possible, and we're doing it. However, these are different implementations.
Yeah.
So for instance, Lucene lookup takes normally about 1 millisecond, and a graph traversal, like a hop between two nodes, takes you do between 2 and 4 million hops per second. So that's 1,000 hops is what a traversal costs you, an index lookup. And an index lookup doesn't scale as well as a graph local traversal. That's the basic point in RDBMSs that have both, by the number of joins you have to do, you have more index lookups, and by the number of primitives or records you have, these things get harder to optimize, and they get slower.